Now we consider surface. If omega is an open subset in Rn, and the f is a function C1 function defined over omega, and the p is a point in omega. So this is omega, and the p is a point in omega. Okay, such that fp is 0. Without loss of generality, we assume that fp is 0. Then we consider all points whose value is 0. So the set fx, that is fx1 xn is 0. The points x satisfying this condition is a subset of omega. In particular, p is a point satisfying this condition. So this set is f equal to 0. Okay. Sometimes we call it a level set, or p is here. So no. In some condition, under some suitable condition, from this equation, f equal to 0, fx1 xn equal to 0, you can express xi for some I. Xi can be expressed from the other x, x1, xi minus 1, xi plus 1, xn. Okay. Therefore, xi is a function of the other variables. This means near the point P, in the neighborhood of P, our set, that is f equal to 0, the point satisfying s equal to 0, near the point P, is the graph. This part is the graph of a function phi. No. The portion of this set f equal to 0 near P is a graph of this function phi. Phi is a C1 function of this C1 function phi. This is the content of the implicit function theorem that we will establish later, but we use this fact here. So, as a graph of a smooth function, of a continuously differentiable function, it is considered as a smooth hypersurface. This portion we denoted by S. So this portion denoted by S is a smooth hypersurface. Here we said hypersurface because our dimension n might be greater than 3. So it is not a surface in the usual sense. Therefore, it is called hypersurface. So we want to find the normal vector of the hypersurface. So here is the S. S is this part. S is here. This is S. Part of f equal to 0 near the point P, and the normal vector perpendicular to this surface n. We want to determine this n. That is the normal vector of S at the point P. We want to find normal vector to S at the point P. How to compute this normal vector? This is our question, okay? So to solve this question, suppose this is our S and P is here. We consider a curve. If gamma minus epsilon Rn is a curve, C1 curve passing P. So the image of this curve is this. So this is our gamma, the image of gamma. And the gamma itself is a map from, a map from minus epsilon gamma. Okay? This curve, we say this is a curve on S. Gamma is a curve on S if the image of gamma contained in S. In this case, we denote gamma minus epsilon. Since its image is contained in S, we can consider this as a map from minus epsilon to the subset S and subset of Rn. That is our S. Okay. So that is gamma t belongs to gamma t belongs to S, and S is a subset of f equal to 0. Therefore, f gamma t is 0 for any t in the interval. Okay? So what can we do? Using this condition, and the curve is passing through P, this means gamma 0 is P. So we can take the derivative, because f is differentiable. F is C1, therefore differentiable. And the gamma is also C1. So by the chain law, the composition f gamma is a C1 function. Because f is real valued. F is omega 2r. Okay? Therefore, the composition is C1 real valued one single variable function. It is differentiable. We take the derivative at t equal to 0. What we get? Because the composition is actually a constant function, the value is 0. Therefore, by taking derivative, we see that 0 is the derivative at t equal to 0 of the composition, which is the gradient of f at the point P, and the inner product with the derivative of gamma at 0. Okay, this formula we mentioned in our last lecture. After our corollary of the chain law, we have emphasized this. Now we use this result, so we get this equality. But gamma point 0, this what's this? This is the tangent vector to the curve gamma at the point P. This is okay. So we find that for any such gamma, our gradient of f at P is orthogonal to the tangent vector. This means that all the tangent vector of the curve lies in a plane, hyperplane, perpendicular to the gradient. Okay, because the inner product is 0, so our gradient is this vector, which is orthogonal to the tangent vector of any curve on the surface passing through P. You consider another curve, another curve maybe here. Then the tangent vector is here. Maybe I use another. The tangent vector is here. This tangent vector for another curve is also perpendicular to the gradient of f at that point. This means all the tangent vector of the curve on the surface passing P lies in a plane. This plane we call the tangent plane. This hyperplane is called a tangent plane of the surface at the point P. And the gradient of f at P perpendicular to the tangent plane is called the normal vector. So this is the normal vector at P. Okay. So using the chain law, we obtain our deserved result. We can find the normal vector for surface. So this is quite important. Now we consider an example. Suppose S, our f x y z is x squared plus y squared plus z squared minus 1. So f equal to 0 is the surface, is the sphere, unit sphere. In R3. Okay. This we denote by S. R3. So upon the P, the coordinate is x0, y0, z0 belongs to S. Now we find the tangent normal vector. We will find the normal vector at P of the sphere at P. Let's see what's this. So the gradient of f at P, the gradient of f is 2x, 2y, 2z. Therefore, at the point P, this is 2, maybe 2x0, y0, z0. Twice of the position vector. Point P here on the sphere, from the origin, from the center of the sphere to the point P on the sphere, we have a position vector. This position vector is proportional. This is the position vector. This position vector is proportional to the gradient of f at P. So this means the normal is the same in the same direction of the position. This is we know for the sphere this is true. So this justified our previous general argument for the general surface. And our discussion is about n-dimensional for any n, even n equal to 2. When n equal to 2, for this example, it is the circle. Okay, this is also true. So this is the method to compute the normal vector of a surface given by f x equal to 0, or in coordinate form. Maybe I will write a summary. Normal vector at P in the surface f equal to 0 is the gradient of f at P. Okay, so this can be considered as a geometric meaning of the gradient. Of course, to be a normal vector, you should be non-zero if the gradient is not 0. If the gradient is 0, you could not say that the 0 vector is a normal vector. This makes no sense, because for 0, the 0 has no specific direction. So you cannot say 0 is a normal vector. Okay, so we need to assume that the gradient is not 0. Okay, we assume this condition. So this is the case of surface given by an equation. Surface given by fx1 xn is 0, or simply write fx is 0. For such a surface, it is very easy to find the normal vector at any point. Just compute the gradient of the f at that point. Okay, this is quite easy.